Ever really looked at a simple grain of salt and wondered, what on earth is holding that thing together? Well, it turns out it's an incredible story of attraction, of theft, and ultimately of a surprising kind of stability. Today, we're going to pull back the curtain on the ionic bond, a chemical connection that's way more like a dramatic heist than some friendly handshake.
Right, let's just start with something we all have in our kitchens, table salt. Seriously, what is that invisible force, that glue that holds those tiny little crystals in their perfect cubic shape? The answer is hiding in a really fascinating chemical process, and we are going to break it all down. Now, in the world of chemistry, you probably hear a lot about atoms sharing electrons. That's a covalent bond. It's like a cooperative partnership. But that is not what we're talking about today. No, we're talking about something totally different. We're talking about an outright theft, a complete transfer of an electron from one atom to another. And that is the heart and soul of the ionic bond. So, what's the deciding factor here? Why do some atoms play nice and share, while others just take what they want? Well, it all boils down to one fundamental property that every single atom has. And that property is called electronegativity. The easiest way to think about it is as an atom's greed or desire for electrons when it's near another atom. Some atoms have a pretty weak pull. They're not too bothered. But others have an unbelievably strong pull, almost like a superpowered magnet for electrons. So check this out. It's basically a spectrum. If the difference in that greed between two atoms is really small, they share the electrons pretty equally. No drama. If the difference gets a bit bigger, the sharing becomes unequal, like a chemical tug of war. But what happens when the difference is massive, when it's greater than 1.9? Well, at that point, sharing is completely off the table. A total transfer is about to go down. And this, right here, brings us to the main event, the electron heist. And to understand any heist, you've got to meet the key players, the stars of our little table salt drama. Okay, in this corner we have sodium. Sodium has this one single, lonely electron in its outermost shell. And frankly, it's kind of an inconvenience. Sodium would be so much happier if it could just get rid of it. And in the other corner, we have chlorine. Chlorine has 7 valence electrons, and it is desperate. I mean, truly desperate for just one more to feel complete. And here is the whole reason the heist is even possible. The difference in electronegativity, in that electron greed, between chlorine and sodium is a whopping 2.23. That means chlorine's pull on electrons is overwhelmingly, incredibly stronger than sodium's weak little grip. It's not a fair fight at all. So picture it. The moment these two atoms get close to each other, it happens in a flash. The super electronegative chlorine just yanks that lone electron away from sodium. And in that instant, everything changes. Sodium, having lost a negative electron, suddenly has a positive charge. And chlorine, having gained one, now has a negative charge. Now, normally, after a theft, you'd expect the two parties to go their separate ways, maybe call the atomic police. But in the wild world of chemistry, something completely unexpected happens next. You see, that very act of theft didn't create enemies. It actually created the perfect conditions for a powerful, lasting connection. By becoming opposites, one positive and one negative, they've set the stage for a brand new relationship. Because we all know the rule, right? Opposites attract. The new positive sodium ion and the new negative chloride ion are now powerfully, irresistibly drawn to each other. It's a force called electrostatic attraction, and that attraction is the ionic bond. They're held together, not by sharing, but by the powerful force of being complete opposites. But wait a second, you might be thinking, why did sodium just give up its electrons so easily? Was it really a victim here? Well, the truth is, sodium got something amazing out of this deal too. The answer lies in the ultimate goal for pretty much all atoms, something called the octet rule. You see, atoms are at their most stable, their most happy, when they have a full outer shell of 8 electrons. It's like reaching a state of perfect contentment, just like the super chill noble gases. So let's look at chlorine first. It got what it wanted, right? By gaining that one electron, it went from 7 to a perfect 8 electrons in its outer shell. Bam! Just like that, it has the same stable electron setup as the noble gas argon. For chlorine, the mission was a total success. But here is the brilliant twist in our story. What about sodium? By losing that one inconvenient electron, the shell underneath it which was already full with 8 electrons, becomes its new outer shell. So by losing, sodium actually won. It also achieved a full octet, becoming stable just like the noble gas neon. It wasn't a one-sided crime at all, it was a win-win, a benevolent heist where both atoms came out on top. So we have this stable pair, a positive sodium and a negative chloride, locked together. But the story doesn't just stop with 2 atoms. Oh no, this is where we zoom out and see the really big picture.
Now, you might be thinking, okay, so they form a little molecule. That's what we usually expect from a chemical bond. But that's not what happens here. This process is about to build something vast, organized, and beautiful. Instead of just making a bunch of separate little partnerships, this attraction creates a massive, repeating, 3-dimensional structure. It's called a crystal lattice, and this is where the real magic happens. Think of it like a giant 3D checkerboard that goes on and on. Each positive sodium ion gets completely surrounded by negative chloride ions, and each negative chloride ion gets completely surrounded by positive sodium ions, building outwards in this perfect, repeating pattern. And this magnificent, ordered structure, this crystal palace, is exactly what you're looking at when you see a grain of table salt. And this strong, rigid structure is what gives ionic compounds like salt their unique properties. It's why salt is a solid at room temperature and has a super high melting point. You need a ton of energy to break up that powerful grid. It's also why salt water can conduct electricity. Once dissolved, those charged ions are free to move around and carry a current. So we started with a simple grain of salt, and we found this incredible story of a so-called theft that was actually a win-win deal, creating perfect stability and this incredibly ordered structure. It really makes you wonder, doesn't it? If something that looks like a crime on the surface can actually be the foundation for such perfect order, what other unexpected, counterintuitive forces are quietly building the world all around us?